topic 8,
Systems of linear equations. Pow, 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 pow.
To kick things off, we gotta talk about what a system of equations is. Oh, look, a definition. It's a group of two or more equations. Normally, or in this unit, we're going to be looking at linear equations in two variables. And we could call a system of linear equations just a linear system, just to make things easier.
Nice.
In this unit, we're going to look at different ways to solve that linear system. We're going to look at graphing, we're going to look at substitution, we're going to look at elimination. But first of all, we're just going to look at what a solution is going to look like. So, a solution to a system of equations is the set of all xy coordinates such that that xy coordinate is a solution to all equations in the system. It is not enough just to be a solution to one of the equations.
What?
It has to be a solution to all of the equations. So, what we're going to do is we're going to look at different examples and see if the given point is, in fact, a solution to the system provided. So, what we're going to do is I'm going to just say, you know what, let's call this top guy equation number 1 and this next guy equation number 2, just to kind of clarify things. When we solve or try to determine whether that point is a solution to our linear system, we are going to plug that point into our first equation, we're going to plug it into our second equation, and see if it satisfies those conditions. So, we're going to check equation 1. When we do this, we actually have to break our equation up into our left-hand side of the equal sign and the right-hand side. So we write LHS for the left-hand side and RHS for the right-hand side. My left-hand side for equation 1 is just the y value, okay? And in my point, my y coordinate is -2, so we'll just plug in -2 there. And we want to continue all the way down until we end up with a single value. On our right-hand side here, we have x minus 5, and our x value in our point is 3, so we have 3 minus 5, and we again continue on until we have a final value, which is going to be 3 minus 5 is -2. And what we want to do at the end is we want to compare our left-hand side and our right-hand side. If our left-hand side equals our right-hand side, we know that that point is going to be a solution to that particular equation. In order to be a solution to that whole system, it has to be a solution to all of the equations. So we also have to check equation number 2. We do the same thing. We split it up to left-hand side and right-hand side. On my left-hand side of my equal sign, I have 2x plus 3y. When I see an x, I'm going to plug in that 3. When I see a y, I'm going to plug in that -2. And I'm going to keep on going until I end up with a single number. So I get 0 for my left-hand side. On my right-hand side of that equal sign, I just get 0. My work there is done. My left-hand side does in fact equal my right-hand side. And since those are all of the equations in my linear system, then whoop, whoop, the point 3 comma -2 is a solution to this system. What? Yeah.
Neat. That seems so easy, even Mr. A could do it. Here I go. So I've got these two equations. Oh, let's do a straight inverse of colors. I'll call this equation 1. I'll call that equation 2. All right. I'm going to check this in both. I'll check. Oh, I don't know. Let's start with equation 1. And thereabouts I've got a left-hand side, and I've got a right-hand side. Where's my left-hand side? 4x plus y? Okay. But x is -1, and y is 6. Neat. My right-hand side is 2. Oh, that's already good. All right. Left-hand side is equal to right-hand side. I guess I've done this whole thing, right?
Oh, no you aren't.
What? Why?
You have to check all of the equations in the system.
Oh my goodness. I could have ruined everything. All right, I'm going to check equation 2. My lachis and my rachis. I've got a 2x plus y on this left-hand side. Again, plugging in -1 for x, plugging in 6 for y, and seeing what I get. Doo-doo-doo, doo-doo-doo, doop. And my right-hand side is 3. Oh no! 4 is not the same thing as 3. My left and right aren't equal. In this case, then, I will have to say that this point is not a solution to the system. Because sure, it's okay for equation 1, but it's not okay for equation 2. Is sad.
All right, looking at example 3, we're going to do the same thing. We're going to label equation 1 and 2, and we're going to start just straight up checking them. So when I start checking my equation 1, I again break up to my left-hand side and my right-hand side. On my left-hand side of equation 1 is just y, and y in this case is equal to 1. My right-hand side is 3x minus 7. My x in this case is equal to 3, and 3 times 3 minus 7 is 9 minus 7, which is 2. Whoa! My left-hand side does not equal my right-hand side. This is so sad. The thing is, when we are checking to see if a point is a solution to the entire system, as soon as it doesn't satisfy one of those equations, we don't actually have to check the rest.
What?
So if we know that the point 1 is not a solution to equation 1, we can then say the point 3, 1 is not a solution to the system without even having to check equation number 2. 3, 1 is not a solution to the system.
Neat. We're also going to look at developing equations from contextual situations. We're not going to actually solve these particular scenarios, but we're going to create the system of equations that models each scenario. When we do that, we're going to have to choose and actually specifically define the variables we're using. And when we choose our variables, we want them to be meaningful variables. We don't just want to use x and y for the sake of using x and y. They should be linked to what we're actually finding. And then, from the information provided in the context, we'll create our equations. Like in this one, Kira is 2 years older than Desiree. Oh, and 3 years ago, Kira was twice as old as Desiree. What are their ages? Now, we're not actually solving for this. We're not going to find their ages right now, but we are going to determine that system of equations. We're going to model a scenario. Key thing we are finding here is their ages. That's the thing we're after. So when we choose our variables, that should be the basis for it. I'm going to use a K for Kira. But when we write this down, we're not going to say, how do you spell? We're not just going to say let K represent Kira. Like Kira's what? Kira's height? Kira's number of toes? I don't know. This is specifically going for Kira's age. And similarly, I'm going to use D for Desiree. And not just saying let D represent Desiree. It's specifically her age. And now we can start playing with these. Look, I need a highlighter. What color do I want? This bluish one? Sure. Kira is 2 years older than Desiree. So if that's the info I'm playing with, then that's what's going to give me equation 1. And equation 1 says Kira is, so Kira's age, is, that's her mathematical equals, 2 years older than Desiree. So if we take Desiree's age and we add 2, to make it 2 older, we'll get Kira. So then we can take Desiree's age and increase it by 2. 3 years ago, Kira was twice as old as Desiree. So that's going to give me my other equation. So Kira's age 3 years ago was 2 times Desiree's age 3 years ago. There's Kira's age 3 years ago. Here's Desiree's age 3 years ago. But Kira's age 3 years ago isn't the same as Dez's age 3 years ago. It's 2 times that. And that is how that equation is built. The end.
Whoa, cool.
It is.
So we could do the same thing in different contexts as well. So in this case, we have a company and they had to pay $816 in wages to 2 of its employees who worked a total of 52 hours that week. Whew! One employee made $14 an hour and the other made $18 an hour. How many hours did each employee work? So just like what Mr. A said before, we could kind of figure out an idea for what our variables are going to be based on the question that we're asked. The question says how many hours did each employee work, so that's going to give us a really big hint of what our unknowns or our variables should be. And we're not given the names of these employees, so realistically we could make up variables that we think will suit the situation. Why don't we let, let's say A represent the number of hours worked by the $14 an hour employee. So, couple of things when we're thinking about what our let statement's going to be. We can't just say let A represent the first employee, because what about the first employee? Her height, her fashion sense, right? We need to say, no, not really. But we have to say, well, we're looking for the number of hours she's worked. So we are going to make sure that that's included. Also, we aren't told the names of these employees, so we have to distinguish between the 2 of them. So the way that we distinguished between this first one, to make sure it's clear, we said that this first employee, A, is the $14 an hour employee. Okay, so that is just used to distinguish between our first variable and our soon-to-be second variable. I'm going to let B represent the number of hours worked by the $18 an hour employee. Right, so now I know that A will represent the number of hours worked by the 14-hour employee, and B represents the number of hours worked by the $18 an hour employee. Whoop, whoop, whoop. Alrighty. Now we have to look back at the information provided and see what's kind of relevant here. So a company had to pay $816 in wages to 2 of its employees who worked a total of 52 hours a week. One employee makes $14 an hour, the other makes $18 an hour. Wonderful. Seems all relevant to me. But the first thing that kind of sticks out is that the wages should probably go together, all of the stuff that is money related. And the other value that's given to us is a total... Oh, I didn't want that. Yikes.
Do better.
Okay. That there was a total of 52 hours a week worked by those 2 employees. So that information is going to give us equation 1. In equation 1, if the total number of hours worked that week by those 2 employees is 52, then A plus B should be 52, because A is the number of hours worked by the first employee, and B is the number of hours worked by the second. Now, highlighter. Ooh, green. The other information says that, well, there's a total of 816 in wages for its 2 employees, and one makes 14 an hour, one makes 18 an hour. That information there is going to give us equation number 2. Well, we know that we need to include our variables in there. So if we're thinking that the total amount spent on those or paid out to those 2 employees is $816, well, how much is paid to the first $14 an hour employee? Well, she gets $14 times the number of hours she's worked. So 14A. And our B employee gets $18 an hour, so the amount of money she's paid, or he, is 18 times the number of hours they worked, which is B. So that information there will give us our 2 equations. We have equation 1 and equation 2. And there we have it, our linear system.
I feel like if this purple was lighter, it would remind me more of Easter. It actually kind of does remind me of Easter.
It reminds me of, like, what children think grapes look like. You know, if you had, like, a grape...
Oh, I meant, like, the whole, like, the entire color palette together.
Jaffiel.
Yeah.
Okay.
You get a very Eastery vibe. Connie and Jed have decided to go for wings with friends. Aw. Connie orders 12 wings, 1 bevy for $10.10. Jed orders 20 wings. Ooh, he hungry. And 2 beverages. Oh, he thirsty. For $18. What is the price of each wang? Where's my highlighter? Highlight. We're after the price of each wing and each beverage. Yes, I'm using this one. Let. So we need the price of each wing, the price of each beverage. I'm going to go with W for wing. And again, I'm not just saying let W represent the wings, because it's a particular aspect of those wings. It's representing the price of a single wing. And B, also a price. And then we start playing with this info. Info we know. Ooh, decisions. What does this do? I don't like it. I'm going with it. Light stuff. Is it this? Alright. So this is for equation 1. 12 wings, 1 beverage is $10.10. So, if you take 12 wings and 1 beverage, it's going to cost you $10.10. Just note, to be fully simplified, we're not going to write this one coefficient, so it's best to just write that as B. 12W plus B equals 10.10. As long as I'm going ugly colors here, how could I ruin this further? I
Pick that gross yellow.
This gross yellow? Jed orders. Oh yeah, this is going to be revolting.
Not the math, the colors.
No, math is always beautiful. That's a known fact. That's going to give us equation 2. And that one says, if you get 20 wings and 2 beverages, you're going to pay $18. Yeah, I'm just going to leave it like that. This pleases me. Oh, wait, that's all I need to do. I just need to develop the equations. Well, that's these equations developed. Should we practice this?
Yeah, I'd say so. I mean, we've got the time.
Yeah, we do. In that case, I personally would recommend maybe pages 400 to 402. Possibly all the questions.
You know what? I would say probably not all of them. I'd go number 2 to 6, 8, 11, 13, 16, and 17. Just off the top of my head here.
Okay. Yeah. Yeah. Question 7, do you think?
7? I mean, if you really want to, sure, but not totally mandatory.
Okay. Question 1.
Again, live your best life. Do what you gotta do.
Question 26.
Oh, baby, why did we not write that down?
I honestly don't even know if question 26 exists.
Well, and that is part of your homework.
Yeah, that's for you to discover and report back to us so that we know. Ask us all the questions, comments, concerns you may have, and believe in yourselves and believe in the dream.
Peace out, homies.
Adios, muchachos.